Welcome to my channel. In this video, we're going to learn how to differentiate all types of functions. So normally functions are of the form y is equal to a x raised to power n, where a is a constant and n is the power. So if this is the case, then to differentiate, we'll just involve confirming how y changes with respect to x. So we refer to that as dy dx. And to do that, the first thing you're going to do is pre-multiply the function by the power. So you'll have n times the function that you have, that is a x raised to power n. Then the next thing is to reduce the power by 1. So minus 1. So remember the procedure is pre-multiply by the power. In our case, the power is n, and then you reduce the power by 1. So let us see how we can do that in real examples. So the first example, required to differentiate y is equal to x raised to power 3. So the equation is y is equal to x raised to power 3. So for you to get dy dx, in this case, you will pre-multiply by the power, and the power is 3. So you have 3 times x raised to power 3, and then you reduce the power by 1. So what you'll have there is 3x, 3 minus 1, that is 2. Then for the second example, where you have y is equal to 4x raised to power 5. So dy dx will involve multiplied by the power, that is 5 times 4 x raised to power 5, then reduce the power by 1, so that you have 5 times 4, that is 20, then x raised to power 5 minus 1, that is raised to power 4. Then for this other example, example 3, y is equal to 3 over 4 x raised to power 2. So in this case, dy dx will be given by 2 times 3 over 4. It's 2 times 3 over 4 times x raised to power 2 minus 1. So this is 3 over 2. If you simplify that, we get 3 over 2 times x raised to power 1, which is just the same as x. So let us look at more example. So there's a situation where you are required to differentiate a constant. So let's say that the constant is of the form y is equal to a. So for you to differentiate a constant, it is better if you rewrite it as a complete function. That is where there are two variables, y and x. So you can rewrite this as y is equal to a times x raised to power 0. And remember from the laws of indices that any number raised to power 0 is the same as 1. So actually, you have not changed the equation at all. It is still adding up. You have just rewritten 1 in terms of x raised to power 0. So if that is the case, you will perform the differentiation as you would for a normal function. So as usual, you will take dy dx by multiplying by the power. So in this case, the power is 0, and then you multiply by a, then you reduce the power by 1. And remember, these are products, and one of the terms in the product is 0. So if you multiply any number by 0, you will obviously get a 0. So this just tells us that if you differentiate a constant, you will always end up with a 0. So let us look at the various examples that we have. So example 1, differentiate the function y is equal to 10. So you have y is equal to 10. And like I said, it is better to write this as a normal function, just that the x is raised to power 0, so that dy dx is 0 times 10x raised to the power 0 minus 1. So you'll find that because you have multiplied by the 0, then the answer there will be 0. So it does not matter what the nature of the constant is, whether it is a fraction, whether it is a big number. If you differentiate that, you are supposed to get 0. So for example 2, you have y is equal to 4 over 5. So you write that as y is equal to 4 over 5 x is power 0. So that when you get dy dx, you are going to multiply by the 0, and it means your answer is going to be 0. The same applies to number 3, y is equal to 100. So you write it as y is equal to 100, x is power 0, and you get dy dx to be equal to 0. So let us look at this category of functions. So you can get a function which we refer to as simple fractions. So in a case like this, you will actually apply the laws of indices to rewrite the function. So remember, according to the laws of indices, if you have 1 over a number a raised to power n, then you can rewrite that as a raised to power negative n. So we're going to employ this relationship to rewrite the function before we can actually differentiate that. So it means therefore that you can write this as y is equal to a times x raised to power n with a negative there. So after this, you can just differentiate this as you would a normal function. So dy dx will be multiplied by the power, that will be minus n times a x raised to power negative 1 n, then you reduce the power by 1. So that is all you need to do actually. Just rewrite the function in this form, and then just perform the differentiation as you would for a normal function. So let us look at the examples that we have. The first one is given as y is equal to 5 over x raised to power 3. So just use this law of indices. Just write this as y is equal to 5 x raised to power negative 3, so that you just differentiate what you have normally. We multiply by the power, that is negative 3 times 5, which will be negative 15, and then reduce the power by 1, so negative 3 minus 1, and that will be negative 4. So if you like, you can leave the answer like that, or you can rewrite it in this manner, so that you have a negative 15 over x power 4, which is positive in that case. So for the second example, we have y is equal to 4 over 5 x squared, which you can write to be 4 times x raised to power negative 2, but it's still over 5. So we just differentiate this normally. So that is dy dx is equal to, you pre-multiply by the power so that you get negative 8 over 5 times x, then you reduce the power by 1, so that is negative 2 minus 1, that is negative 3. So again, you could leave the answer like that, or you could rewrite it as negative 8 over 5x cubed. So you could be required to differentiate sums or differences of various terms. So what you'll do is you'll handle each and every term independently, and then you add them or you get the differences. So you'll just use the methods that we have used for all the single terms, and then you combine whatever you get there. So let us look at this example. The first one, y is equal to 5 x raised to power 4 minus 2 x raised to power 5 minus 7 x raised to power 3. So for this case, dy dx will be, you multiply by the power, that is 4 times 5, x raised to the power of 4, reduce the power by 1, then do the same for the second term there, that is 5 times 2, x raised to the power of 5 minus 1, minus 3 times 7, x raised to the power 3 minus 1. So you'll find that this will be 20 x raised to the power 3 minus 10 x raised to the power 4 minus 21 x raised to the power 2. So it's just a matter of handling each term independently and then using the signs between them. If it's a minus, you subtract. If it's a plus, you just add the terms. So for this other example, dy dr, remember, it is not a must that all the functions will be in terms of y's and x's. It could be any other letters. So like in this case, we have y in terms of r. So we get dy dr as being equal to 3 times 20 r raised to the power 3 reduce the power by 1 plus 4 times 1 over 4 r power 4 reduce the power by 1. So you'll have 3 times 20, that is 60. Then r raised to the power 3 minus 1, that is r raised to the power 2 plus 4 times 1 over 4, that is 1 times r raised to the power 3. Then for this example 3, dy dx will be given by 20 times negative 1 over 2 reduce the power by 1 minus 9 times 1 over 9 x raised to the power 9 minus 1 plus, remember what we said about constants, they have a variable x or whichever variable that is relevant to that equation. So like in this case, we have x's, so it means there is x here, just that it's raised to the power 0. So if you multiply by the power, that will be 0 times 20 and x raised to the power 0 minus 1. So if you simplify this, we're going to have this minus 10 x raised to the power 19 minus 1 x raised to the power 8 plus 0. So you just write it as negative 10 x raised to the power 19 minus x raised to the power 8. So there are certain times when you can have a function which you can simplify first before you get its derivative. So we refer to those as fractions reducible. So if you meet a case like that, you first of all simplify it before you can actually differentiate. So in this case, you can simplify this. If you look at the numerator, we have a complete square. So you can use factorization method to factor it or to factorize it so that you see what cancels the denominator. So in the numerator, you can factorize this by looking for two numbers whose sum is the same as b. So you look for two numbers whose sum is the same as b, and b in our case is 4, and their product is the same as a times c, that is 1 times 4, which is just 4. So you'll realize that those two numbers are 2 and 2. So what you do, you just rewrite this as x squared plus 2x plus 2x plus 4 over x plus 2. So you'll have the common factor between these is x. So x into x plus 2. Then you expect x plus 2 this side. And for you to have obtained 4, it means you multiply 2 by 2. So plus 2 over x plus 2. So we can see that in the numerator we have x plus 2 times one of these, that is x plus 2. Then that is over x plus 2. So x plus 2 and one of these x plus 2's will cancel, so that what we are left with is y being equal to x plus 2. So this is what we are going to get its derivative, or this is what we're going to differentiate. So like I said before, it is safer to write this as y is equal to x raised to power 1 plus 2x raised to power 0, so that dy dx is the same as you multiply by the power, that is 1 times x, it is the power by 1, plus this, you multiply by the power, times 2x raised to power 0 with the power by 1. So you'll find that this is 1 times x raised to power 0, and x raised to power 0, according to the laws of indices, is the same as 1. So you have 1 times 1 plus, you have multiplied by 0, so that is 0. So that your final derivative is 1. Example 2, you are required to differentiate y is equal to x minus 3 times x plus 1 times x minus 1. So this is also reducible. It means you can expand this before you can differentiate. So we could multiply manually, where we take this times this, then whatever we get times the other one. But we can use what we call the quadratic identities. Look at that last term there. It appears as a plus b times a minus b. And according to the quadratic identities, this is always a difference of squares. So it means, therefore, that y is equal to x minus 3 times x squared minus 1 squared. That is x squared minus 1. So you can expand this so that you have x into x squared minus 1 minus 3 into x squared minus 1. So that this is x cubed minus x minus 3x squared plus 3. So you can rewrite this equation as x power 3 minus 3x squared minus x power 1 plus 3x power 0. So that when you differentiate this, we want to have 3x, you reduce the power, that will be minus 1, and 2 times 3x power 2 minus 1 minus 1 times x 1 minus 1 plus 0 times 3x 0 minus 1. So if you simplify this, this is 3x squared minus 2 times 3x, that is 6x, and this is 1 times x to the power 0, that is 1 times 1, so minus 1. And this is 0, so we leave it at that. Example 3, we are required to differentiate y is equal to x into x squared minus 1 over x plus 1. So all we need to do is to simplify this particular fraction before we can differentiate. So if you look at the numerator, there is x squared minus 1, which you can write as x into x squared minus 1 squared over x plus 1. So remember, x squared, 1 squared is the same as 1. So there's no change that you have made there. So if you look at what is in the bracket, it appears as one of the quadratic identities, that is the difference of squares. And according to the difference of squares, that is the same as a plus b times a minus b. So it therefore means that we can write y as x into x plus 1 into x minus 1 over x plus 1. So since there's a multiplication between these terms, you're allowed to cancel x plus 1 and x plus 1, so that y is equal to x into x minus 1, which you can rewrite by opening up the bracket as x squared minus x. So this is now what you differentiate. So you'll have dy dx, you multiply by the power, reduce the power by 1, you do the same for this, 1 minus 1. So this is 2x minus this 1 times x raised to the power 0, that is 1 times 1, which is just 1. Example 4, we are required to differentiate y is equal to the root of x into bracket x raised to the power 2 over 3 minus x raised to the power 1 over 2. So you can simplify this. You can actually rewrite the root of x using the laws of indices. According to the laws of indices, the root of a number is the same as that number raised to the power half. So it means that what we have here is x raised to the power half into x raised to the power 2 over 3 minus x raised to the power 1 over 2. And then according to the laws of indices again, you are going to have to multiply x raised to the power half times whatever is in the bracket. So remember, these bases are the same. So you can use the laws of indices, where if you have a raised to the power n times a raised to the power m, you have a raised to the power n m. So this will be the sum of the powers, sorry. So that will be a raised to the power n plus m. So here we'll have x times that will be, just add the powers, 2 over 3 minus, do the same for that, that is x power half times x power half, that is x power half plus half. So that this is the same as x raised to the power 7 over 6 minus x raised to the power 1. So now this is what you are going to differentiate. So dy dx in this case will be multiplied by the power, that is 7 over 6 times x raised to the power 7 over 6, reduce the power by 1. Do the same for this, that is 1 times x raised to the power 1 minus 1. So we're going to have 7 over 6. Then 7 over 6 minus 1 is the same as 1 over 6 minus x raised to the power 0, which is just 1. So there's another category which requires us to apply certain rules, like a case where you have to differentiate a product of two functions, you'll use what we call the product rule. So if you have two functions, say f of x and g of x, and both of them are differentiable, that is, their derivative exists, then for you to get the derivative of their product, you will get the derivative of the first function, you multiply by the second function, plus the first function multiplied by the derivative of the second function. So let us look at this example. We have differentiate y is equal to 6x cubed minus 10, minus x into 10 minus 20x. So what you're going to require is identify the two functions. That is, the first function, that is f of x, will be the first function, that is 6x cubed minus x. And what you're going to do is you're going to obtain its derivative. So if we differentiate this, we're going to get 18x power 2 minus 1. And then identify the second function, that is g of x, as 10 minus 20x. And you get its derivative as minus 20. So now you want to get dy dx, that is the derivative of the product. So dy dx in this case will be the derivative of the first function, that is the derivative of f of x, that is 18x squared minus 1. Then you multiply that by the second function, and the second function in our case is 10 minus 20x. And whatever you get, you add to the first function, and the first function is 6x cubed minus x. You multiply that by the derivative of the second function, which is negative 20. So all you need to do is just open up the brackets. So you're going to have 18x squared into 10 minus 20x minus 1 into 10 minus 20x, then minus 20 into 6x cubed minus x. So let us simplify this. This will be 180 x squared minus 360 x cubed minus 10 plus 20x minus 120 x cubed plus 20x. So now all you need to do is just collect the like terms. So we can go with the powers. So we have power 3, that is minus 360 x cubed and 120 x cubed. If you add the two, you're going to get that to be minus 480 x cubed. And the second part, we are going to look at the ones with the power 2, that is just 180. So plus 180 x power 2. Then the next one is just 20x plus 20x, that will be plus 40x. And then there's the constant term, which is just 10. So there's another rule called the quotient rule. You apply this rule if you are dealing with a fraction or a quotient of two numbers. So if the two functions, f of x and g of x, are both differentiable, that is, each of them has a derivative, then if you want to get the derivative of their quotient, you'll use this formula where you take the derivative of the first function, multiply by the second function, and you subtract the first function times the derivative of the second function divided by the square of the second function. So we have an example where you are required to differentiate y is equal to 3x plus 9 over 2 minus x. So the first thing you need to do is just identify g of x and f of x. So you can say that f of x is the numerator, which is just 3x plus 9. And you can get the derivative of that first function by just differentiating this. And you're going to get that to be 3. Then you can let the second function, g of x, be 2 minus x, for which you can get its derivative to be negative 1. So now that you have all the requirements there, just substitute these into the formula. So dy dx, that is the derivative of this quotient, dy dx, will be given by the derivative of the first function, that is 3, multiplied by the second function. The second function is 2 minus x, minus the first function, and the first function is 3x plus 9, multiplied by the derivative of the second function, that is negative 1. And then you divide that by the square of the second function. That will be 2 minus x squared. So let us simplify that. It will be 6 minus 3x minus 3x, not minus 3x. You have a negative 1, so negative 1 times that will be plus 3x, and then you'll have plus 9 all over 2 minus x squared. So in the numerator, you have 6 plus 9, which is just 15, and then minus 3x plus 3x, that is 0. So in the denominator, you have you have 2 minus x squared. So you could open that up, expand it, or you can just leave it like that. So there's another rule called the chain rule. So if you have a function of a function, that is when you use the chain rule. For this case, let us look at this. If y is equal to f of u and u is equal to g of x are differentiable functions, then for you to get dy dx, you're going to take dy du times du dx. So it means the first thing you're going to do here, in our example where you're equal to differentiate y is equal to 3x cubed plus x squared raised to the power 6, is to rewrite this in terms of u and g of x. So this can be written as, you can let the inner function be u. So that is u is equal to 3x cubed plus x squared. And if that is the case, then you can get du dx. Just differentiate that. You're going to get that to be 9x power 2 plus 2x. So if 3x cubed plus x squared is u, it therefore means that the function that we have is y is equal to u raised to power 6. And you can get the y, the u from there. You multiply the power, that is 6, u raised to power 5, which you can just write out to be 6 into u, and u is 3x cubed plus x squared. So now you have all the tools that you require. You can easily get dy dx. So dy dx is just dy du, which we have here as 6 into 3x power 3 plus x squared times du dx, and our du dx is 9x squared plus 2x. So you could leave it like that, but if it is simplifiable, you can just simplify it. But in this case, that is how we are going to leave it as x cubed plus x squared into 9x squared plus 2x. Or you can multiply by 6 so that you have 18x cubed plus 6x squared into 9x squared plus 2x. So if you like, you can open up the brackets, or you can just leave it like that. So you can be required to perform a differentiation from the definitions, or from what we call the first principles. So we have an example: differentiate y is equal to x cubed from first principles. So we can trace this using the Cartesian plane, and let's say we have the curve y is equal to x cubed to be like that. So along the curve, there are 2 points, that is point A and point B. So let's say that you're at A, and the coordinates are x and y is given by x cubed. So remember, if you move along the curve from point A to point B, there will be some changes in x. So we'll represent that small change in x by delta x. So it means at point A, we have the coordinates x and x cubed. And then you move to point B. After some movement from A to B, there will be some small change in x. So it will also affect y, because y is expressed in terms of x. So it means, therefore, y will be the x that we have cubed. That is what the function requires us to do. Then if we have those 2 points, we can differentiate from first principles. That is, dy dx can be given by the limit as this small change in x. Remember, if you move towards B, there's a point where A will be on B, and the coordinates will be the same. So it means that small change in x will actually tend to 0. So for you to get dy dx, you get the limit as that small change in x tend to 0 for change in y over change in x. So therefore, what we need is to obtain this change in y over change in x, which is basically just obtaining the gradient, or just the gradient function. So between A and B, we can get that gradient. We take y2, in our case, y2 is x plus small change in x cubed minus y1, which is just x cubed, over x2, which is x plus the small change in x minus x1, which is just x. So you are required to expand this so that the difference will be clear. So you could use any method to expand this. So if you expand this, you're going to get x cubed plus 3x squared change in x plus 3x change in x squared, and plus that change in x power 3. But you have a minus x cubed there, over x minus x is 0, so you're left with change in x. So it means in the numerator you have x cubed minus x cubed is 0. So you have 3x squared, change in x, plus 3x, change in x squared, plus the other one, that is just change in x cubed, and that is over change in x. So now you have the change in y over change in x as this, that is 3x squared times delta x plus 3x times delta x squared plus the cube of delta x over delta x. So you can factor out the common factor in the numerator, that is delta x into 3x squared plus 3x delta x plus delta x squared, and that is over delta x. So delta x and delta x will cancel, so that you're left with 3x squared plus 3x delta x plus delta x squared. And remember, dy dx is given by the limit as small change in x tend to 0 of dy dx, and our dy dx, that is the change in y over change in x, is 3x squared plus 3x delta x plus delta x squared. So what this means is that as A moves towards B, the small change in x will eventually be 0. So therefore implies that every function within this term here, every term within this function that bears the change in x will eventually become 0. So it means, therefore, the only term that will be left after that is the one without the change in x, and that will be our derivative from first principle. Okay, so at times you can be required to show the application of differentiation. So one of the applications of differentiation is in kinematics, that is things to do with the linear motion, where we have acceleration, velocity, and displacement. So let us look at this example. A particle moves along a straight line such that its displacement s meters from a given point is given by s is equal to t raised to the power 4 plus 3t squared plus 4, where t is time in seconds. Determine its displacement, velocity, and acceleration when t is equal to 4 seconds. So for the displacement, all you need to do is just substitute t, and t is 4. So for displacement, you're going to have s is equal to 4 raised to the power 4 plus 3 into 4 raised to the power 2 plus 4. And that is the same as 4 raised to the power 4 is 256 plus 3 times 4 raised to the power 2, that is 48 plus 4. And you're going to find that to be equal to 308 meters. So for the other part, that is the velocity. So for you to get velocity v, you're going to differentiate displacement with respect to t. So you're just going to differentiate this, so that is 4t raised to the power 3 plus 2 times 3, that is 6t plus 0. So after that, we're just going to get velocity when time is 4. That will be 4 into 4 or 3 plus 6 into 4, which is going to be 4 times that, that is 256 plus 24. And that is going to be 280 meters per second. So now for the acceleration, you get acceleration by getting the derivative of velocity with respect to time. So remember, we had obtained velocity as 4t cubed plus 6t. So if we differentiate this, we're going to get 3 times 4, that is 12, t squared plus 6. So it means acceleration when time is 4 seconds will be 12 into 4 squared plus 6. So that is going to be, this is 192 plus 6, which is just 198 meters per square second.